Okay, guys, we're going to go ahead and get started. What I wanted to do today, if you watched the last video, it was a video of the PowerPoint presentation. Towards the end of that, we had some of these logic circuits, and we turned the logic circuits into Boolean expressions. I want to practice that today. I sent out an email. Hopefully you got it. Had a chance to print out the documents that I want to go over today. If you didn't, I'll put it up on the board. You can just get pen and paper. Make sure you have pen and paper. We'll kind of work through a few circuits. I'm going to show you how to do a proof with a truth table, and that'll be it for today. And then also I'll put up, probably today or tomorrow, I'll put up a copy of the manual. Some of you have already probably got it, ordered the manual, but I'll put that cover up so you can see it, and then the website to download the simulation software. So what happens is that if you start with the problem, maybe you walk in, you have some kind of automated system that you want to write a program for, which is going to go into a PLC. The PLC is going to control the automation in the factory. You're given, you can write down in prose or some kind of description in words the way or the functionality you want the program to have, and then you go from words to these logic circuits, and you can go from logic circuits to Boolean expressions, and then from that you can go to what you put in the PLC, which is called ladder logic. In reality, you can go directly from the circuit to ladder logic, but in a couple of weeks I'm going to show you how you can, if you leave it as a Boolean expression, you can actually there's techniques you can use to minimize the logic that you'd have to come up with to control a situation. So what I want to do today is practice going from this circuit to a Boolean expression, and it's pretty simple if you remember your ands and nots and all of that. So let's take out pen and paper. We'll go through. If you have a blank paper, maybe just copy the circuit down, and I don't know if you guys want to. I'll tell you just go ahead and work it, and then I'll give you a chance to do each one of these, and then we'll go in and we'll do it together. We'll kind of do this one together if you want to. The way I did it on the PowerPoint is we just kind of look at what we have at each portion of the circuit. So this is an AND gate. Remember, the AND is shown by the operator. It's a dot operator. So that dot means and this is an OR. So if I was ORing two variables together, I would show it with the cross like that. With AND, you can treat AND as if it was multiplication. So you know when you multiply, you don't really have to put that dot there. It's understood to be there. Well, it's the same way there. If it's if you're ANDing variables, you can leave that operator out, and it's understood to be there. And any way you can show a multiplication with variables, you can show ANDing. So in other words, if you want to put a parenthesis there, that means AND. If you want to put two parentheses there, that's another way to write AND, and so forth. So let's go ahead and if we did this first one together, what you do is you come in here. I think of these variables as actually going through the gates. If they go through the gates and they don't hit a bubble, remember that bubble, the state indicator, basically it puts a knot over the top of the variable. So as long as I don't hit a bubble, I just come straight through the gate, and I'll give it whatever operator corresponds to the particular gate it goes through. So for example, the A and the B go through the AND. So at this point, I have A dot B, and C is like right here. And then the two go together. I got this. I take this as kind of, I'll put this in parentheses. I take that kind of together. A dot B will come through, and I'll have A dot B. That's an OR, so it's ORed with C, and I'll set that equal to either X or Y or something like that. So that's what I want to do for the rest of these circuits. Now you really don't need these parentheses. There is an order, a precedence, an order of operation like with regular algebra. So it's understood that if you were going to do this, I can take this away. And it's understood that you would AND these two together first before you OR, just like regular algebra or arithmetic. So you don't have to put the parentheses in there, although sometimes I do it just to make it clear. So for this first one, that's what you would get. So what I want you guys to do is do the other three, and then I have a couple more I'll put up there. We'll do those. And then I have another sheet where I think we're given the expression we want to go to Gates, and then we'll do some De Morgan, and then I'll show you a proof. We'll probably get done a little early today, and that'll be it until Friday. So go ahead and do this next problem. I'm going to make some room on the board. And if you have any questions, just go ahead and open your mic and let me know, and I'll answer your question if I can. I don't know if this green marker is showing up. Hopefully it is. So if you're doing this, when you get right here, that's an OR gate. So you're going to get A. You're going to OR that with B. So that's right here. And then you're going to AND that with C. So I got C and set that equal to my variable, which is X. So that will be the expression for that one. And you guys go ahead and do the other two. And then I'll put some more on the board while you guys are working the other two. That's 5, 6, so we got one more. All right, so here, again, I go through the gates, I'm ANDing, and here, inside of here, I got A dot B, but when it hits that bubble, I nod it. So you got the inversion of A and B. So I show that like this because of the bubble. So that's at this point. At this point right here, I still got C, and I got to go through an OR gate. So I'm going to end up with A, B, bar, and I got to OR that with C and set that equal to X. And then this one at this point, again, you got a bubble there. So that's an OR gate. So I go A, OR, B. When I hit the state indicator, the bubble, it knots it. Excuse me. And then I got to AND that with C. Now, if you wanted to, you can actually just put the C right here because that bar acts like a grouping symbol. It's equivalent to a set of parentheses. Now, I usually don't like to do that because I think when you put the parentheses in there, it just makes it a little bit more clear. But technically, if you wanted to, you didn't have to put the parentheses there because you can't do anything to this. You can't multiply or distribute the C inside that bar unless you do some other manipulation to it. But that was what you get when you set it equal to X. So that's for that one. Now go ahead and do these two. And if you have any questions or if I do something wrong and you catch me doing something wrong, just open your mic and let me know. do the two top ones, and I think we got one more to put on the board. Okay, so the one in the upper left, if you did that one, you should have added here. Right here we got A dot B, so we got AB. At that point, here we still got C, and here we still got D. Then I got OR. I gotta take the AB, and I gotta OR that. So I'm taking this whole thing, and I'm ORing it with C. And I gotta take that whole thing, all of that, and I gotta AND it with D. So I'm just gonna use a bracket right here, put my D there, and set that equal to X. So I'm using brackets and parentheses just like you would in regular algebra. So I think that's correct, what I have there. And then this one, at this point, I take A and B and I OR it. And then here I got C, but right here, this inverter is going to make this D naught, so I flip it. So I end up ANDing all this together. I end up taking A or B and ANDing that with C and D. This should be a D naught. When I hit that inverter, it's a D naught. And that's going to equal Y. Seems like I left a gate off of that, but I guess I didn't. I just copied this off the, my printer stopped working, so I think I copied that circuit right. I don't have the actual diagram, so hopefully that's what the problem looked like. This one right here is actually kind of important. Anybody recognize this as anything? I mean, I don't know if you can look at it and tell what this is. Anybody?
Light switch.
Say it again.
The two switch light switch.
Okay, well, yeah, you could use it for that, definitely. What function does it represent? Because the light switch you're talking about is actually, you can implement with this logic function I'm talking about. Can anybody look at this and tell? Let's get the expression and see if you can tell. I will say you'll use this circuit. You will use this. If you don't recognize what it is, it turns out to be pretty important. So anybody get the expression? Anybody work it? What do you get when you work it out? I know about. Go ahead. Somebody's gonna say something or not? So right here we got what? Go ahead.
A times not B. Plus not A times B.
Exactly. So that right there, you should be able to look at that and tell what that is. But if not, I'll let you think about that. But he's exactly right. Through here, I got A, but it's inverted because I go to the NOT gate. But the A can also flow here, so I got an A down there going to that AND gate. Likewise, I got B here, so I got a B coming in there that's non-inverted. So at this point, I got A bar B, and at this point, that's not right. I drew my circuit wrong. This should actually go over like this. So at this point, I got A, I got B bar because of that, and that's where he gets the A, B bar, and this takes the two and ORs them together. So what that is a representation of this. If you go back and look at the logic for this, that's what that represents. And this turns out to be pretty important in PLCs. There's something called an interlock. An interlock is a circuit designed to make sure something doesn't happen. And so this comes into play when we talk about interlocks. So we'll get to that at a later date. So these should be pretty easy. If I quiz you on them or give you some kind of test on this, I think that's pretty simple. Nobody should have any issues with that. Now, if you look at the other handout, they give you, I don't even know if we have to do all of these. I think once you do one, you can do them all. But let's just do one or two of these. Given an expression, you want to go back to the gate circuit. So if you have the other handout, go ahead and take it out. If you don't, I'll put the problem on the board. You can just do it right now. It's pretty simple. But you should be able to go back from the expression. From the expression to the gate circuit. So you're going the opposite way. And the first one I have is, I guess I wrote this down right. I hope I did. I got AB or B, CD, or E, F, G, H. So we want to take that and get the circuit for it. And so all you got to do there is, of course, these terms right here, think of these as terms. Every term equates to an AND gate, and then you have the pluses in there that equate to OR gates. So if every term is an AND gate, I got three AND gates. I got a two input AND gate. I got a three input AND gate. Now notice that I have B here and B here. One way to do it is to show the AND gate like this and just connect that up like that to B. You can do that if you want to. Personally, I don't like doing it that way. I guess it makes sense to do it that way, but I think it's cleaner if you just repeat B. But you got more lines if you do that. But I just like to repeat it. So I'm just going to repeat B, C, D. And then I got this four input gate. So 1, 2, 3, 4. And I got E, F, G, H, E, F, G, H. And then for each one of these, that's an OR. So I got to take that and OR together. And so I bring it in there like this. And there's my gate. So what we can do, there's symbols in the PLC that represent all these gates. And we can actually implement this in the PLC using ladder logic. It's pretty simple to do. So that's one of them. And then the other one, you had this. You had A cross B. You have C, D, E crossed. And then you have F, G, H, all the way out to I. So here we have terms. We have, think of products. Every product is an AND gate. So I have three sets of AND gates up there. Or three input AND gate, I'm sorry. So I have here, I have this, OR together. I have a three input OR gate. I think I said AND gate, but I meant OR. So 1, 2, 3, and that's E, D, C. The order doesn't really matter. And then I got a four input, which I'm not gonna draw all the way out. You know what the variables are. But then here I got, these are dots. So that means I'm taking those and I'm adding them together. So that would be the circuit. And then usually letters at the beginning of the alphabet you use for inputs. and letters at the end of the alphabet like X, Y, Z used for outputs. And the variables are always uppercase. And I think that's it. So nothing to write home to mom here about. This is pretty simple. There is one thing that's important though. Want to make sure you can do it. And the ones I have on the practice sheet are pretty easy, but it can be kind of complicated, demorganizing. Demorganizing is really, really, really important. And I'll try to show you why. Maybe I'll show you why today, we'll see. But if you remember De Morgan, that's where they say you can write any kind of logic using and, or, not, so you can use those. And you can see equivalencies of circuits. So for example, they give you this. And they want you to, oh, I can't even say it. They want you to demorganize it, and then they give you a for variable. So that's what I'm saying. If you can do one, you can do the other one. That's what I'm saying. But basically, this is the break the line, change the sign thing that I told you about. So go ahead and demorganize that. Now the gate for this one, if you make the gate, it's just a 3-input AND. And then to get that not, you put a bubble there. So that's what that is. But if you demorganize it, you can write the logic of that in terms of an OR gate, basically a negative OR gate. So you want to break the line, change the sign. So if I break the line, I get this. I break the line. And I change the sign. So that's saying that or this is equal to an OR gate with the inputs knotted. Like that. Anytime you have the bubble on this side instead of the output, this is a negative. This would be a negative of whatever the gate is. So this is a negative OR. If I had the bubble here, it would be a NOR. So that's how you would do that. And this, I mean, it's the same thing. Just break the line, change the sign. And I think, we'll do one of the other ones. But I think when you see one, you can do them all. This is just really kind of trivial stuff right here. We'll do one more. The other one was where I had this with a bar over it. So you break the line, change the sign, you end up with individual variables that's OR together like that. So this turns out to be important. It's kind of hard for me to tell you why until we get into programming, which will be here in a week or two. But then you'll see why we have to be able to do this. When you get a little bit more familiar with the ladder logic, I'll show you why we have to be able to do this. Without it, you wouldn't be able to program the PLCs the way they're designed today. So that's pretty simple stuff. Now, this other thing I want to do, and this is where students have a little trouble, not because it's hard, but because they don't show enough work, to use a truth table to do a proof. So the last thing I want to show you, did I press record? Yeah, I did. Okay. I forgot. Somebody told me they wouldn't be able to make it. I want to make sure I'm making a video, but sometimes I forget to hit that record button, and I end up not making a video. So I want to know if this, let me put it over here. If this is, and this means logically equivalent to this, are these the same? And how would you show that they're either yes, they're the same, or no, they're not the same? So how would you show that? Well, they want you to do a proof. And the way you do a proof is with the truth table. What I'm going to do, I got two variables, so I'm going to have 4 rows. So I got A, and I got B, and I'm going to make a truth table. And so remember the way I said number the truth table. You're counting in binary, but if you start here, you alternate every other bit. So I start counting at 0, and I go 0, 1, 0, 1. and then 0, 0, 1, 1. That gives me all the possible combinations. And then what you want to do, now there's a couple ways you do this, but I like to kind of show everything. So when you guys, if I give you one of these on the quiz, don't skip any steps. I want to see every column here, and you'll see what I'm saying in just a second. The first thing I want to do, I think the easiest one is this. I'm going to do that one. And when I do it, I'm not going to do the whole thing. I'm not going to say A, B, bar. You could. You guys are smarter than I am, so you probably can go right to it. But I'm going to just do A, B. I'm going to AND A and B. If I AND A and B, and I know an AND is only true where I have two inputs that are true. For every other combination, it's false. So that's A and B. And what I mean by show every column, once I got A and B, now I can go ahead and knock that column. I can say, all right, now I'm going to get A, B. I'm going to take that, and I'm going to invert it. So if I invert it, I get a 1, 1, 1, 0. And that's the binary value of the right side of this equation. So now I want to see if the left side has the same bit pattern. If it does, they're logically equivalent. If it doesn't, they're not. And again, I'm going to do this one at a time. So the first thing I'm going to do is just get A naught. I already got A, so A naught is easy. I'm going to get A bar. A is 0, 0, 1, 1. So here's going to be 1, 1, 0, 0. And B bar, B is 0, 1, 0, 1. This will be 1, 0, 1, 0. And so when I get those two, now I'm going to take those and I gotta AND those. For my final step, I'm going to take these two columns and I'm going to AND them. And so if I AND this and this, I get a 1. If I AND this and this, I get a 0. This and this gives me a 0. This and this gives me a 0. So I compare this and that. If they're the same, that means these are logically equivalent, but you can see they're different. So the answer is no, these are not logically equivalent. So what I'm going to do for you at some point on the quiz, you have to work it out, and you got to show, you want to show definitely show this, show every column in the truth table. And it's pretty easy if you do it that way. Sometimes students will go, they'll leave all this out and go right to you got to show me, I should be able to see your reasoning, how you go from each one of these through to get to the final answer. I should be able to see all the steps, is what I'm trying to say. So it's not hard, but it might take a little practice. So go back and watch this video if you forget how to do it. I don't know when I'm going to quiz you over this, but at some point you got to show me you can do this. And I think that's really all I had. You guys have any questions you want to ask me? Any concerns, issues, things we need to talk about? Anything you want to say? Has anybody gotten their lab manual yet or the software? Anybody got that stuff yet? Well, nobody's saying anything. Are you guys still there?
I haven't got mine yet.
All right. All right, guys. Well, I'm done. That's it. So if you don't have any questions or comments, that's it. I don't know Friday if we're gonna do another live stream, or I gotta see if it's a PowerPoint. But you guys have a great rest of the day. If you need me for anything, you know how to get a hold of me. Just send me a text and we can work it out. Have a great rest of the day, and I will see you later.